Ja, en twee zo.
Nee,
Cloud en Google. Op ons woord hebben we twee. Want dan wil je niet vrij worden en dan weet je niet zeg ik maar heel informatie. Dat daar moet ook
streaming kind of Okay, everyone, grab a seat. There's still some few seats on this side. Okay. I'm really excited to have Frank here today because I only knew from his blog post and they really inspired me to implement some of the graph algorithms that he talked about. And actually, it turned out they were really fast. So good job. So Frank will talk about scalable graph algorithms, and I'm excited. Right? So please switch on your microphone and thank you, Frank.
So yeah, I'll be talking about some what I think is some neat stuff. I want to say research. So this is I would describe this sort of open source research as open source products and stuff like that. So bear that in mind a little bit. A title slide comes up. This looks a little ridiculous. It looks so ridiculous on my laptop. Like I'll pretend I'm trying to develop my personal brand or something like that. But the title slide will come up in just a moment if you're wondering why I had to put my name in big letters. Hopefully someone got a photo of it. So let's start with a motivating problem. Hopefully it motivates people. Maybe it doesn't, in which case, no worries. You are a person who likes to look at social signals. This is a stream of data coming at you. I'm going to pretend that it's tweets, right? Because everyone likes tweets. There's got to be money there somewhere. I'm sorry, I'm historically from around Silicon Valley, so a lot of the things I'm going to say involve this fascination, right, that I'll have a big dump truck full of money at some point. I don't know. But think of this as social good, otherwise. Big unit, dump trucks full of social good that are being delivered. So people, when they tweet, they talk about things, right? There might be topics that they use to indicate some sort of content. There might also be mentions of people. So when you tweet, you might talk about other individuals who are communicating. And this is neat. This gives us a little bit of data that has some structure to it, potentially some graph-like structure, and that people talk at one another. This is basically similar sort of data that Vasya had mentioned earlier in her talk you heard for that. So here's some questions you might ask, right? And I'm going to claim that some of these we know how to do, we're pretty comfortable with. So if someone wants to know what's the most popular hashtag, the topic out there that most people are talking about, well, we can rest assured that people are good in doing that for us. We can make it a bit more exotic though, right? We could say, I don't want to know about the most popular topic across the entire corpus. That's boring. It's going to be Justin Bieber. That's not interesting. I want to know instead by some sort of emergent structure of the communication that's going on. So if I look at this graph defined by whom is talking to whom, and I'm going to pick connected components, but we can argue about whether that's a good example or not. What are the most popular topics within each of these connected components? Right? So some people start talking about something we don't know, but let's try to find out by looking in there and seeing what's popular. And everyone here is a graph person or interested in graphs. So let's imagine that you have an idea. Someone plopped a few gigabytes of Twitter data in front of you. You could pick that up and turn it into a graph and go and figure out component structure, and then do some aggregation. Excellent. The place we're going to go in this talk is what if your boss came and said, no, I need this now. Actually, I want you to take this stream attached to it and keep all of this data current with millisecond latencies as fast as possible. If it turns out to be second latencies, that's fine, but we're really going to be trying to look at how can we avoid recomputing things over and over from scratch. How can we react more or less immediately to changes in our input data collections. So that's what this talk is going to be. What I'm going to show you for most of the talk is this data parallel programming framework. It's a cool framework. It's going to be really simple. Unlike a little bit of the earlier talks, it's actually going to look a bit more like SQL. There's no capital letters, so there's that. It's going to be general enough to express graph computations relatively naturally. It's not going to be 200 pages of anything. I'll show you some examples to the side. But, and there's a comma here, this property has a really cool property that everything automatically updates when you change the inputs. So you write your programs in a particular way, it's great, they go and they run, they're not particularly slow, not quite we call them fast yet, but they all have the property that if you change the inputs, the outputs change automatically to the new correct insert. With absolutely no ambiguity, no weird race conditions or timing or anything like that. It's a project, you can go and grab it. The main thing that I would warn you about is it's all in Rust. That's different than what most people use, but it's awesome and delightful. Everyone should learn Rust. That's a different talk. So let's walk through what this looks like. This is an algorithm that we heard about earlier in Vasquez's talk for finding the connected components in a graph. So if someone gives you, this is this label propagation algorithm, so I'll state it verbally first. Every node in the graph gets a label, typically it's their own name initially, and then repeatedly, until we find some sort of fixed point combination, each of the nodes propose their label to each of their neighbors and say, look at this neat label. And the node then collects all the proposals that have come and say, what's the best label? We're going to take the minimum in this particular case. What's the smallest label? And if you do this often enough, repeatedly have all the nodes propose to their neighbors, and have all the neighbors collect proposals, you eventually converge to the connected component structure because the smallest label in any given component floods through the component and everyone gets that value and then they stop talking about this. So I've written that down in this particular language that we're going to be looking at, this thing called differential data flow. And it's basically, these sort of, I don't call it SQL, but things like joins and concats and group bys, maps and filters, and a pretty cool operator that shows up here called iterate, which is not too complicated. I think it's an operator that starts from a collection. Right? So you have a collection of labels perhaps that it started with, and it takes a function. Okay? So this is a function from some initial set of labels to a new set of labels. And it will repeatedly apply that function. Here we're just taking the set of labels, we're hitting the labels with the set of edges, we're doing a join to propose for each node the label that it has to each of the neighbors. We throw back in the initial set of labels because you should be allowed to keep your old label if you want. You don't have to get a new proposal. And then we take a minimum to try to figure out for each node in parallel what label would it like to keep. So this is, it's a program. You could write that, and you could imagine running this in your favorite big data sort of setting. This wouldn't be too exciting. It would be delightful because it's so simple and concise, and everyone understands exactly what's going on. But let's talk about this a little bit. Here's a different way that I could try to describe the computation. I've basically taken each of the operations that I've done here and turned them into these little boxes, and I'm going to build a data flow graph. So I'm just going to start putting edges in each time we use one of the bits of the graph. So for example, we use edges both the example above to personify the map. This is how we get our initial labels. We also use a set of edges in this join operation when we communicate labels to other nodes in the graph. And if you sort of follow through, I think I've gotten each of them right. The map goes into this labels variable that we use both in the join and the concatenation. There's the minimization, and then that feeds back to the labels. Often we like putting together data flow graphs because then we can deploy the data flow graph to a cluster and we can do a big data thing, and that's great. But there's another really cool thing that goes on here, which is the data flow graph tells us who's actually using each of these bits of data. So if one of them changes, for example, like let's imagine change happens to edges, we can track down what actually needs to get fixed or corrected in the computation. If an edge change, we can say, well, we'll need to fix this join for sure, and we'll need to fix the map, and we can start pushing updates through this data flow graph. Not rerunning from scratch, but just fixing the things that are broken. That's pretty informal, and I'll try to be a bit more precise, but if you imagine this magical world in the future, and we're going to get there hopefully in the next 40 minutes or so, that has this magical property that for each of these operators, we're able to maintain the invariant that the output of the operator is always equal to the input to the operator, even as we start changing the inputs. So the operator sort of self-correct or self-repair automatically. We get a pretty cool property. If I've drawn a lot of loops and weird edges and stuff here, but if that were true, then we could have this nice data flow description, declarative I like to call it, but description of connected components where we're allowed to change the edges arbitrarily, and the labels that come out the bottom get automatically repaired as we go. It sounds a little magical maybe, but we'll build up to that. Some of these things people know how to do already. Some of them are new and exciting here. This is ridiculous. Okay, great, good. Let me tell a little bit more of a story now, though. So one of the things that I want to try to convince people about is that it's actually valuable, potentially valuable, to think about your query using this type of language, these very simple operators that are automatically updated. I'm going to give a few examples where we can do something really cool. Basically, we're going to get back to that motivating example from the introduction, just using a few more boxes up here. So imagine, if you will, we start with some tweets. The tweets have, each of them have at least 3 things. Let's say a user, some topic, and you might mention someone else. So we can pretty quickly pull out the users and the mentions from each of these tweets and feed them into our connected components computation from the previous slide. And coming at the bottom, we'll get a whole bunch of user and label pairs. These are, both of these are users, but for each user, some label indicating what component it's in. So that's great, that's great. And as tweets come and go, and we add tweets, and maybe tweets get retired because some window has expired, we'll see changes coming out the bottom of the connected components computation telling us how these labels have changed. That's neat. What do you do with that? Well, one thing that you can do with that is take the tweets, again, up to the side and ask for each user, what topics have they mentioned? So this is, again, just a map operation where for each tweet that flies by, we pull out the user and the topic. And then we can join these two and say, oh, well, we have for these users and topics, we have users and labels, we can join. We get a whole bunch of now labels and topics. It's pretty cool. So for each connected component out there, there's some sort of topic got mentioned in a tweet somewhere. At which point, we start to do things like aggregation. We can go and ask topic A type things where for each label, what are the most popular topics with that label? So this is not just by user anymore, but across the entire connected component, what's the most popular, let's say, top 5 things that people are talking about? Great. Okay, so that, imagine that this works, and we'll get there. But this would be a lot of fun, right? As tweets fly by, you get to see as they change the most popular topics for each of the connected components out there. But let's make things a bit more exciting, we're going to sort of backfit some of the capabilities of what I've been describing to cause a weird new thing to happen, or a cool new thing to happen. So in addition to this computation hung up of all these tweets, I'm going to make a new data set, a new collection called queries. We're of course going to imagine that these are going to be queries that people fire at the system, but just think about it as a collection for the moment containing Twitter handles that we're actually interested in. Here's this is mine. And the idea is that we want to ask our system here, our computation, what's the most popular topic in this person's connected component? Right? So we can do some of the same things that we've done before. We can join the outputs from the connected components computation to figure out the label of the component that I'm in. Yeah. And we can join that again with the label topics from the top K to say, well, here are the 5 most popular topics for the component that Frank shared. And if we believe all of the magic that I'm trying to tell you about, as the queries collection changes, things happen automatically and quickly, then all you need to do is throw in another query. Just add one more username in there. It will trickle through the data flow graph. We'll figure out, what should we join it against to get the label? What should we join the resulting label against to get the top topics? And it all happens surprisingly quickly. We're not rerunning big horrible queries from scratch. We're essentially just doing a few lookups in key value stores that are hidden behind some of these operators. Moreover, lest you actually go and try to use a key value store, we have some delightful properties of consistency here. So I've done 2 lookups into the key value stores. First to find my label, then to find the most exciting topics. And you'd have a horrible nightmare of a mess if you actually kept these in 2 separate key value stores and tried to get consistent reads out of these things and make sure not to accidentally screw up and show someone something they shouldn't have seen. So, but this will all just work out. It's nice. So this is what I'm promising. At the end of the talk, there'll be just a quick little demo. So there's that. But I thought I'd try to walk through some of the explanation for how this works out, what makes it possible. So I'm going to build up to this differential data flow thing, starting out with incremental data flow, which is a fairly well understood, or at least it's been around for a while, approach in the database community and processing community. And the general idea is you have a data flow graph. It's big and there's lots of it, but we're going to look for the moment just at an operator in the data flow graph. And the way the operator works is that some data shows up. And the data, in our case, is going to be some actual payload, like a record, and a weight, which says something like, yeah, there's 1 of these, or maybe there's 2 of these, or who knows. Lots of these show up. Sorry, this isn't just meant to be a single datum, but lots of them show up. And the operator is then, has some logic, so the operator is like, well, let me think. I'm going to produce some output, we'll call it Y here, which is also some data and some counts. So, sorry, it's a set of these pairs, data and count. So could be gigabytes of data. I don't know. And then it's going to ship it downstream to the next operator, which does approximately the same sort of thing. It looks at its input and it does a bit of work. So this would be great if we were in some sort of MapReduce or Spark style acyclic graph where the edges only go to the right, but we're not going to do that. We're going to do something a bit more exciting where now changes happen. So a new bit of data arrived, and what's this? What's this thing here? Our model is going to be it's a difference, right? So it's a dx, it's a change to the original collection we had. It's still going to be a bunch of records and weights, though the weights can be positive, it can be negative, pretty flexible. The annual change shows up, and we're now meant to think of the input as the sum of these two things. Right? So I've added my diff in here, and I want to figure out what sort of diff should I produce on the output to bring this into balance. And I'm just going to do some math by pictures here, right? So we're trying to produce some output that has the property that when you add it up, again, because that's what the downstream person expects, when you add it up, it should be equal to the operator's logic applied to the initial collection, and this is the cunning bit of like preschool mathematics that I'm using to describe some complicated data flow stuff. So basically, we add these things all together and we apply our logic to it, and then we subtract off anything we've sent already, because we've already sent it, and we don't need to amend anything that's already right. And we solve for the question mark. And having done that, we have a dy that we can send down. So this repeats. You want to get some more differences. We'll do the same sort of logic again. We'll accumulate everything up now and subtract away the first two things and get a new dy. And this repeats as much as is necessary. Each time data show up, some corresponding update goes out. Sometimes the update might be empty. We might get some differences coming in that don't actually require us to change our output at all. That would be nice. It's not usually the case. But. Cool. So if you're writing a stream processor, this is the sort of thing that you would do. As you get more data, you write your little operator to respond appropriately, and all's well and good, and it actually works. If the only thing that you had to do is accept new differences coming in to the input of the software. We're going to have to do more than that for sure. Let me just say a little bit about this connected components example, because this is a good fit. People have also exploited this particular approach to designing computation to deal with iterative computations, particularly iterative fixed point computations, where as the computation runs, essentially redoing the same logic on slightly different inputs. Right? So with our connected components computation, we had labels for each node, and as the computation proceeded around these iterations, the labels for the nodes changed, right? And they get smaller and smaller, and at some point they stop changing. But you can rig this basically in the following way. There might be some sort of dot more data flow nodes out there, but roughly speaking, the differences that come out from the operator make their way through some graph, and come back to be the next round of differences for the input. Right? So if we found, for example, if this is the argument operator, the one that's picking from all of the candidate labels, picking the minimum one, as it produces new interesting changes to its output, those changes will flow around the graph, go through the join, and get proposed now to new people. Right? If I change my label, I'll tell all of my friends, hey, I changed my label. They'll pick up all of those changes and say, oh, that's exciting. Maybe that causes me to change my label, maybe it doesn't. But the process essentially continues and keeps running and running until people stop changing, basically until the diffs evaporate and go away. So this is a fairly standard approach to how you would implement iterative incremental computations on big data flow graphs. There's sort of a problem though, which is, this is great, we've co-opted the incremental updating machinery to do this iterative computation. What happens now if someone changes or wants to change the place we started from? So someone says, I changed my mind, we don't have that edge set, or you don't have these initial labels, you've got some other ones. Well, yeah, sorry. Unfortunately, it's not as easy as just taking the difference and throwing it on the end of the list, right? If, for example, we circulated for a long time and everyone got the label 0, and then vertex 0 says, oh, I changed my mind, my label's actually 5, my mistake. It can take on label 5, that's fine, but all of its neighbors are going to immediately tell it, hey, I've got a 0 for you, and we're just going to go back to it'll be a fixed point, but it won't be the correct answer that we wanted from starting from the amended input. So, there's a nice thing that you can do, which as far as I'm aware, no one else has done before, but it's not, yeah, I was going to say it's not complicated, that's really the wrong thing to say. But basically, there's no reason that we have to put all these in a line, right? there are other spaces that we can fill in this particular case, in a two-dimensional slide. If we want to change the input to our computation, we can think about doing that, but just offsetting it a little bit, saying, this is indeed a change to x, but we're going to put it below x instead of at the end of some long list. And the intuition here now is that we have one dimension. This is dimensions that correspond to iterations, perhaps, of connected components. We can have another dimension, independent, corresponding to rounds of input data. So as the input to our computation change, we have some variation there, and we can vary with both of them. We can talk about, for example, the second round of input as a 0th, first, second, third, fourth iteration as well, and we can start to populate all of these parts of the picture. So, well, what would we do if someone showed us this type of difference? The main thing that we need to do is to figure out what do we produce as output. And we need to tell someone about this change to keep the computation going. We'll do what I think is sort of the natural thing, right, which is to say, well, this difference here changed the first iteration. Let's think about how it changed it. We can again apply our operator to this sort of thing, subtract y off, and we have now sort of space to put it, right? Because we've agreed we can use this extra dimension to put some notes about how things have changed. Obviously, the math that we do is sort of natural. I think subtract the right things, apply the function. All right. And the process continues. More diffs might show up, and now we take a slightly different rectangle. And it's not hopefully a surprising rectangle, but it's different. These rectangles that I'm drawing now have really relied on the fact that I've kept all these differences separate. Right? They haven't been lumped up into one big pile. Just kept them apart so that I can take summations over different subsets of differences. And that turns out to be really powerful, right? If we wanted to investigate the first and second iterations of this new round of input data, and someone had already gone and collapsed everything up in the top tier together, you're sort of out of luck, right? You'd have to figure out how to pick things apart. You'd probably end up subtracting off all the work that you've done. But by keeping them differentiated like this, sort of indexed by the round of iteration and the round of input, we can pick and choose what things we want to add together and get fairly more concise differences. So everything continues. Hooray. So there's just some animation we have to go through to all agree that this is correct. Good. So what I've shown visually, at least, and there's as much math as you can swallow to try to make this more technically compelling, is that we can take an iterative computation, this top row here, and do these fun iterative incremental updating strategies. But we can also then incrementally update the incremental updates. It's sort of like a second derivative, if you want to think of it that way. Yeah, you probably don't want to think of it that way, actually. Never mind. Sorry. But it all works out. Like the math supports it, and it's a lot of fun. And what it allows us to do, which is sort of nice, is if not very much change here in x, right? If the first step didn't really change very much, hey, maybe there aren't really a lot of changes in the second step either, given that we're reusing the changes that were observed the first time we went through. So these changes can be really sparse, which is really helpful if we want to go really fast. It means we don't have very much work to do. Let me draw some pictures about that. When we're thinking about how these things get implemented, sorry, I jumped transitions a little too fast. Just to bake everything in as much as possible, the bits of data that we're shuffling around, they used to be records and weight, right? With the implicit sort of understanding that as soon as you saw some records and weight, they were good to go. You should act on them right away. We're not going to do that. We're going to do records and weight with a very explicit time associated with them. This is not wall clock time, but it's some notion of logical time through the execution of the program. In the previous slide, this would have been pairs of iteration and round of input. And by keeping the time explicit there, as opposed to sort of implicit in the arrival order, we can take these weird summations over different subsets. This is the really important thing that we're taking advantage of when we do this. So, now some pictures. So data parallel operators, these are at the heart of all of these large-scale graph computations that we end up doing are these data parallel operators that say, I've got a million nodes in my graph. I don't really need you to execute logic for them one by one by one by one by one. You can do all a million in parallel, in principle. And that's great fun because we get lots of computers and things go fast and everyone feels powerful. But there's actually a better property that they have with respect to incremental computation. So we're used to sort of seeing this picture where I go and I put each of these on different machines and I tell you how much I spent on Amazon, and it's a disaster. But here's a different property they have, which is sort of cool. which is that as new diffs arrive, each of these folks can operate independently. That's good. Hooray. If the diffs arrive and there isn't really that much work, yeah, well, that's great. Then nothing changed. So we don't have to do any of the work there. So if someone explicitly shows us the diffs, and there are only 5 diffs across all million nodes, we only have 5 units of work to do. It didn't have to be true. We could have designed non-data parallel operators that were, a total disaster. You'd have to reevaluate the entire computation. If someone had asked, for example, for the median of all the nodes across the computation, median is not a friendly operator. But we didn't do that. We asked for much simpler things, sort of per node logic, or these joins on keys and what have you. More differences that aren't very big. Just to sort of make it feel big. Great. So let me say just a little bit about what's actually going on actually under the hood, or what do we need to do in terms of maintaining state and thinking about what information we really need to keep our paws on. We've got all these diffs for one particular operator, one particular key of this data parallel operator. Think of this as one node in the graph computation. That one node got some diffs coming in, maybe some rounds it didn't get any diffs, that's fine. We're going to sort of stash all this stuff in some per node state, or per key state more generally. And it's really simple actually. We just mash up inputs and outputs and we annotate them with the time, this logical time, again maybe pair of iteration and round of input at which they were received. Whoop. Some new things arrive. It says I'm here at time D. What do you all think about differences and stuff like that? And all that we really need to do when we do this is go through and ask for each of the existing times, how does it relate to time D? Is the time less than time D, meaning when we think about producing new output at time D, should we include x and y in the summation and then differencing? And maybe not. This second one might correspond to the first round of input, but the 17th iteration, right? And we're only doing maybe the third round of input, 4th iteration. So it's not relevant. We hold back these differences. We don't fold them into our logic. We leave them here. They're going to be important in the future. But yeah. So in this case, we would add up x. We'd add up this dx down here, and then we'd add up the new difference on the input. Apply the operator. Subtract off y and the third dy down here, and produce a new output time. And then we just ship it, and it's all great. We need to stash the data that we produce, of course, so that future time e, when it shows up, so we'll have time d around to do the right thing. We need to remember essentially what differences we've sent downstream, and that's important. So that's it for the visual bits of mathematics. I thought I'd show you a bit now about some actual numbers when we turn this on the Twitter fire hose, and some little bits of code to show you what things actually look and feel like. And then, well, let's do that one by one, and maybe people will be very angry at that point and have lots of questions. So this is just some data that we collected. It's actually from a while, 2013. So that's a long time ago now. When we did the math for this in the paper originally, we took a Twitter trace that we had. I was at Microsoft Research at the time. We had it at Microsoft. No one else can have it. I'm sorry. And we plotted a few things here. This is this connected components computation. We're just trying to understand how large these differences are, how many changes are there at different points in the computation. So we have on the very top this stateless implementation. The stateless one is the one that doesn't try to do anything incremental at all. Each time around the loop, it starts over from scratch. It picks up all the diffs and thinks about things. And it has a static, as we go through the numbers of rounds of iteration, it has a static amount of work that it's going to do. It doesn't get any better, it doesn't get any worse as we execute. If we incrementalize this, we get this red curve, and you notice that it sort of ticks up above the stateless thing. This is because the way we're counting things, at least, if your label changes, you have both your new label with a little +1 indicating it's counted up by 1, but you also have your old label with a -1 next to it. So you disavow your previous value, and you have some new data. So we count that as 2 because it actually corresponds to 2 units of data that we're looking at. But you'll notice that after the upward take up initially, it goes down exponentially. This is in a log scale on the y-axis, and that's really exciting. That means that at the very end at least we're going quite fast, and the final 15 iterations basically take no time. There's a cute trick. The green line is a really cute trick that everyone should eventually learn about, but maybe not right now, where you run this label propagation algorithm not just blindly having everyone chat, but you have people who have small values. They get to talk first. which sort of makes sense, right? You know, if people are going to take them in, maybe have the person who's holding onto 0, put them in charge of talking first. They run for a while, and only after quite a while, if you have label 7 trillion whatever, do you get to talk. So that makes things quite a bit better. But the really exciting thing is we went and we took this 24-hour window over a Twitter trace and shifted it by 1 second. So about 1,000 tweets drop out and get added in. And the amount of differences that happen in that whole process is down here as this blue, we call it line, except you can see it's not even connected, which is awesome. Like the third iteration, literally nothing happened, which is great. We didn't even do any work there. And everything else is just sort of in the tens of differences at most. So we've sort of nailed slightly a good way to really thin down and isolate what is the actual work we need to do to correct our computation, given a small 1,000 or so tweet shift in the input table. These correspond fairly nicely to execution times. So if we ask how long do each of these things take, you know, some large number of seconds to do the computations in various different ways. But when we actually get down to doing this differential shift, actually processing this data differentially, it ends up being, I can't remember exactly, but anyway, on the order of 27 milliseconds to respond to 1 second worth of new Twitter data. So that's great. Fully updating this connected components computation, right? So not just sort of updating it or whatever. The correct answer guaranteed comes out the other end. And we now know if something fabulous has happened in the Twitter messaging effort. So this is meant to get you sort of excited. I have some other, well, whatever. You can care or don't care, that's fine. But something different is going on, right? Which is new and exciting. I have, so that was only the connected components computation. I don't have the real Twitter data anymore because of laws and stuff like that. But what I did do instead was make up a random generator for some purpose. And I was going to show you a bit of, well, I'll show you some proof numbers first. But then I'll just walk you through a bit of the code. This is exactly that data flow example from the beginning of the talk where someone is firing a whole bunch of users, mentions, and topics at a supervised system. And each time, in this particular picture, each time they do that, they're only adding, so they load up 10 million initially, and then we're going to repeatedly do +1, -1, +1, -1, adding new random tweets, subtracting the oldest one, just because that gives the smallest numbers, and that was fun. But if you do this, you see, if you can count the number of zeros properly, this is, I don't even have units on here. It's a few hundred microseconds to do each of these updates. So if you want to, someone hands you a new tweet and says, hey, figure out the corrections to the connected component structure and all of the implications that has for the particular people we have in our query set at the moment in terms of their most popular topics, it's a few hundred microseconds. So you can do what you like with this. You can crank up the number of records that you're putting in by a factor of 1,000 if you like. You can put them into even bigger batches and make it a little faster. But basically, it's a very responsive computation. Very responsive computation that is also fairly rich, right? We didn't have to special purpose build any particular data structures, do anything like that. The efficacy of this depends a lot on the computation that you write. If you write median, bad luck. But please just don't do that. So what I thought I'd do next is just show a bit of the code that produces this. The code is actually brand new. I was bored in Zurich Airport yesterday, so I wrote it. And it's not all that horrible. Well, yeah. We'll talk afterwards whether it's horrible or not. It's Rust, right? So it's delightful. It's about, in total, it's 170 lines, some of which, like you'll see, is there's about a bunch of lines of like just importing stuff and doing Rust nonsense. Reading some things from the input about how much data do we. This includes the data generator as well, that sort of thing. So when we look, I just sort of highlight this part here is the left half of that data flow graph at the beginning. So we take a stream of tweets coming in, and we pick out, for example, the users and the mentions, and do the connected components